how many different ways are there to select a team of 3 astronauts from a group of 7 candidates? That's what we're asking here. And this problem has a trick in it that you may not realize, and we'll get into that in a moment, but I just want to set up, not equations, but I want to set up a picture diagram of what kind of thing we're talking about here. Here's my 7 candidates, astronauts A through G. And, I'm sure I could draw some pictures to make this a little more personal for you with, this astronaut's got long hair, and that astronaut came from Australia or whatever. I don't care about that. Let's just call these astronauts letters A, B, C, D, E, F, G. Okay, there's 7 astronauts. I'm going to pick a team of them as an example. I'm going to say astronaut A, you're in. Obviously, I can't pick A twice. There's only one A. So I'm going to say astronaut B, you look pretty good. And astronaut D, we'll take you. So this is one possible group of astronauts. And the question is, how many different groups could you make? Well, let me answer it with a question. Would this be considered another group of astronauts? I didn't do anything different. It's the same 3 astronauts. I just switched their seats around. That does not count as a new group of astronauts. It's not a different combination. So we have to watch out for that idea of repeating ourselves in the selection of astronauts. Simply moving their chairs around is not what I'm looking for here. So let's talk about how many astronauts there are for that first seat. I have 7 choices. And the only rule on the second seat is it can't be the same one as the first. So the second seat, you only have 6 choices. And in the third seat, you only have 5 choices. And we've done this before, but if you have, let's say you picked A for the first astronaut, and then you have 6 choices left for the second seat. Well, that's 1 times 6. But you also could have picked B for the first astronaut, and there's 6 other astronauts now for the second seat. So that would be 2 times 6, and 3 times 6, and so on. Eventually we get 7 times 6, and it's times 5. These are the number of different combinations and arrangements of astronauts that you could have. It's quite a few. But these are also including all sorts of repeats, right? This list right here includes ABD, BAD, ADB, ADB. Am I repeating myself yet? Okay, no, we're good. And then I think I've got DAB and DBA. These are all the different ways I could have arranged the seating of those first 3 astronaut choices, the A, the B, and the D. There's 6 different permutations or arrangements, meaning this 7 times 6 times 5 idea, that's fine, but it's overcounting by a factor of 6. Every single group of 3 has 6 ways to arrange their seats, and I don't care about any of those ways. For me, these all count as one group of astronauts, not 6. So what you have to do here is realize that if I just got, 300 combinations and permutations of astronauts, only 50 of those count as unique. So what we're going to do is we're going to divide this number up here by 6. That's the number of different combinations. Permutations won't matter. Okay, 6's end up crossing out, so I get 7 times 5 equals 35 different combinations of astronauts that are truly unique sets. And you see this would be my answer right here. So this problem comes down to what counts as a different combination. And since it didn't matter what order the chairs are, then you really don't have as many combinations as you might have thought. This is different from another style of problem, which we've also talked about, which is a code problem. In a code problem, if I said A, B, D, that is truly different than the code D, A, B, right? Those are different codes. So that would be a case where you do not divide by a factor of 6, right? You're not trying to, you are trying to distinguish between backwards and forwards codes. Okay, so those are the 2 styles of combination permutation problems that you have to keep your eye on. And honestly, it comes down to whether you're talking about different arrangements or different combinations.